Welcome to Math TV with Professor V. This is the first video in the course Introductory Statistics, and we're kicking things off with Chapter 1, The Nature of Statistics. Section 1.1 covers statistics basics. So what is statistics? There are two main definitions. First one being statistics are facts or data. It could be either numerical or non-numerical. And this data is organized and summarized so as to provide useful and accessible information about a particular subject. Second common definition is that statistics is the science of organizing and summarizing numerical or non-numerical information. And as we study statistics, you'll see that there are two main types or branches of statistics. Those two branches are descriptive statistics and inferential statistics. So let's look at the definition for each of those and then learn how to distinguish which type of statistics we're dealing with in different scenarios. So first branch is descriptive statistics. This consists of methods for organizing and summarizing information. And that's basically where it ends. So descriptive statistics can include the construction of graphs, charts, tables, even calculating various descriptive measures, such as averages, measures of variation, and percentiles. And we're going to see how to do that in the later chapters. But besides that, descriptive statistics doesn't do anything else. So it's just organizing and summarizing info or data. Got it? Okay. Now, the second branch of statistics is inferential statistics. But before we talk about what that is, we need to get one more definition straight, and that is a population versus a sample. So, population, when we talk about population in statistics, that refers to the collection of all individuals or items under consideration in a statistical study. Notice here, this diagram shows if you're talking about a particular population in a study, that's everybody, all individuals who are under consideration. A sample refers to the part of the population from which the information is obtained. And what you'll notice is that we're going to talk about different sampling methods later in the chapter. Oftentimes, it's very difficult to collect data from the entire population. It sometimes is nearly impossible to do so. So what statisticians will do is come up with a sampling design and take a portion of the population and use that as your representative from which to collect data and information. Okay? Population, everybody under consideration. Sample, just part of the population. Okay, so now that we understand the difference between population and sample, we can talk about what inferential statistics is. And that consists of methods for drawing and measuring the reliability of conclusions about a population based on information obtained from a sample of the population. So what does that mean? Basically, you collect data or info from a sample of the population, and then you make conclusions, or maybe you're not able to because it's not reliable, about the population in general, okay? So you're looking at this smaller set, the sample, and you see whether or not you can make inferences, which is why it's called inferential statistics, about the population as a whole. And just so we're clear, a descriptive study, because we talked about descriptive statistics earlier, that may be performed on either a sample or a population, okay? You can have descriptive statistics for either. Only when an inference is made about the population, right, the entire collection in question, based on information obtained from a sample, does the study become inferential. So we're going to look at some examples right now. That way you can kind of solidify the difference between the two branches of statistics in your mind, okay? First, the directions just say classify each of the studies as either descriptive or inferential, and then explain your answers. Okay, so we have here example 1, the 1948 presidential election, table 1-1, displays the voting results for the 1948 presidential election. Okay, so we see the various candidates, how many votes they received, and even some percentages were calculated. Oh me, oh my. So would this be an example of descriptive statistics or inferential statistics? Well, keep in mind, here are the voting results organized nicely in a table. There's some percentages, but there's been no inferences made about the population or what sort of voting habits we see or anything like that. So the answer would be, this is an example of descriptive statistics. Okay, it's just a summary of the votes cast. No inferences are made. Okay, no conclusions or generalizations were made about voting habits of the overall population or anything like that. This is just summarizing a bunch of data. Okay, good. Let's look at another example. Example 2, data from a sample of citizens of a certain country, they're not telling us which one, okay, yielded the following estimates of average TV viewing time per month for all citizens 2 years old and older. The times are in hours and minutes. Q1 stands for the first quarter. So here they're showing various viewing methods. Do you all even know what a DVR is anymore? Do we still have those? Okay. Using internet on computer, watching video on internet, mobile subscribers watching video on a mobile phone. And then they show each quarter, the percent change. The big giveaway here is that the data was taken from a sample of citizens, okay? And they're giving us estimates of average TV viewing time for all citizens 2 years old and older. So the sample of citizens, the data from that sample was used to make an inference about the population of all citizens 2 years old and older. And I don't know why it's making me laugh that they even consider little 2-year-olds in their TV viewing habits, but I mean, they are avid TV watchers, let's be real. So this is an example of inferential statistics. Why? Because the statistics are used to make an inference or a generalization, okay, about the population. Good. So hopefully that helps solidify the difference just so you can identify it while you're coming across various examples of statistics. Okay, that's the end of section 1.1, discussing the two major branches of statistics. Now we need to get into classifying statistical studies. So there's two main kinds of statistical studies. The first one is an observational study. In an observational study, I mean, it is what it sounds like. Researchers simply observe characteristics and they take measurements, as in a sample survey. Like if I were to ask you guys, what's your favorite ice cream flavor? Comment down below. I mean, why not? That would just be observational. The other kind of statistical study is a designed experiment. So that's when researchers impose treatments and controls, and then they observe characteristics and take measurements. So basically think observational study, the researcher is hands-off, they're just collecting data, they're just surveying you. Designed experiment, they're actually manipulating, right? Or imposing some sort of treatment on whoever they're collecting data from. And an important difference to keep in mind is that observational studies can reveal only association, whereas designed experiments can help establish causation. And this is a big thing that a lot of tobacco companies use to get out of lawsuits saying that smoking causes cancer, because Observational studies will show, right, that those who smoke cigarettes have higher rates of lung cancer, but no designed experiments have been conducted where there's actually a control group who are not allowed to smoke cigarettes and then another group that is forced to smoke cigarettes. That's unethical. And then to see who develops more lung cancer, right? So that's one key difference between the two types of statistical studies to keep in mind. Observational can only reveal association or a correlation. We'll talk about that later in the course. Designed experiments can help establish causation. Okay, let's look at some examples, see if we can distinguish between the two. So state whether the investigation in question is an observational study or a designed experiment and justify your answer in each case. So example 1. In a paper in a medical journal, researchers reported the result of a study of methods for treating patients who had advanced heart failure due to ischemic or non-ischemic cardiomyopathies. A total of 1,530 patients were randomly assigned in a 1:1:2 ratio to receive optimal pharmacologic therapy alone or in a combination with either a pacemaker or a pacemaker defibrillator combination. The patients were observed until they died or were hospitalized for any cause. I mean, there's a lot of detail in here that we do not need, but here's what you need to hone in on, okay? These patients were randomly assigned, and based on that assignment, they received a certain kind of therapy or another treatment, pacemaker defibrillator combination. You don't need to know what that means, so don't sweat it, okay? Just understand that things were being done to them, okay? Treatment was imposed by the researchers, and then, it's a little morbid here. Characteristics were observed until they died or were hospitalized. All right. So this is definitely a designed experiment. It's not like the researchers just sat back and watched what was going on. They decided what sort of treatment happened. So designed experiment because I would say the researchers controlled the treatment of the subjects. Okay, that's totally different than for me to just ask patients, what sort of treatment are you receiving, right? Of the subjects. Okay. Second example. The National Association of Colleges and Employers compiles information on salary offers to new college graduates and then publishes the results in salary survey. Okay. So what's going on? Information is compiled on salary offers, okay, to these new college graduates, and then the results are published. It's not as if any sort of treatment is being imposed. It's not as if any of the data is collected after an experiment is being conducted. So this one is just straight up observational because the researchers did not impose any conditions on the subjects. All right, good. Excellent. So that concludes section 1.1. We're going to continue onward into section 1.2. Simple random sampling. So a simple random sample is a sample in which every object has the same chance of being selected. There's two ways that you could create a simple random sample. First one is a simple random sample with replacement. It's a mouthful, so we like to abbreviate. SRSWR. Once selected, the object from the population has the potential of future selection. So think about it this way. Say you have a deck of cards, you randomly draw a card. If you put the card that you drew back and then redraw, that's with replacement. okay? So that's one type of simple random sampling method. The other one, when we just talk about simple random sample, by default, we assume it's done without replacement, okay? So once selected, the object from the population is excluded from future selection. So unless we specify otherwise, assume that simple random sampling is done without replacement. So basically you have a deck of cards, you pick one, you set it aside, and it cannot be chosen in the next selection, in the next draw, okay? In practice, actually collecting a simple random sample is not so simple. So the idea of it using probability is simple in that way, but in practice, it's not so simple, which I always found funny. Okay, let's look at an example here. As reported by the World Almanac, the top 5 state officials of Oklahoma are as shown in Table 1.2. Consider these 5 officials as a population of interest. So we talked previously about the population representing the entire data set that's of interest, right? And typically you have a population that's much larger than 5, okay? But just for the sake of example, to look at how a simple random sample is collected, this is our entire population. These 5 state officials: the governor, lieutenant governor, secretary of state, attorney general, and treasurer. Okay, so A says list the possible samples without replacement, okay? So you're not putting one back once you've picked it. It cannot be chosen 2 times in a row. Of 2 officials from this population of 5 officials. So we're picking 2 from the 5. What are all the possible samples? So you basically just want to come up with all possible pairings. So you could have the governor with the lieutenant governor selected. So I'll just use the letters to abbreviate, G and L. Or you could have the governor with the secretary of state, G and S. The governor with the attorney general, G and A. Or the governor with the treasurer, G and T. Those are 4 possible pairings. Are there more? Certainly. So I did every pairing of the top official with each of the ones below one at a time. Now I'm just going to go in a nice pattern. I'm going to take this lieutenant governor L and then pair it with each of the officials below. So that would be LS, LA, and LT. And then just keep repeating. So now I'll take the secretary of state, pair with everybody below. SA, ST, and then the last one, AT. Okay? So these are all the possible samples. In a sample, the order doesn't matter. So GL is the same as LG. You don't want to repeat both of them. Those are the same sample, okay, of 2 officials. All right, how many samples do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 possible samples. And we were told to select 2 out of 5. Okay, so describe a method for obtaining a simple random sample of 2 officials from this population of 5 officials. So basically it's just asking, how would you go about picking 2 out of these 5 in a way where every single object has the same chance of being selected, okay? So we want to make sure that it's a simple random sample. So how could we randomly select 2 out of 5? I think the easiest thing maybe is just to write the letters, right? They gave us 5 letters. We could write them on little slips of paper maybe, G, L, S, A, and T on slips of paper. Put them in a bag or box or whatever. Shake it good. And then select 2 without looking, right? No peeking, no cheating, or replacing. All right. That's probably the best way. You could also assign each of them a number. And if you had a 5-sided die, you could roll it, but then, that wouldn't work because you don't want replacement. So no, forget that. All right. For the sampling method described in part B, what are the chances that any particular sample of 2 officials will be the one selected? So basically what it's saying is, all right, if you did this, if we wrote all 5 letters on different slips of paper and randomly pulled out 2, okay, what is the chance that it's one of these that we listed here? Well, we made a simple random sample. So every single sample here should be equally likely to be selected. It should have an equal chance of being selected. So if there's 10 samples total, the chance that we pick one of them would be 1 out of 10. Okay, so 10 possible samples, each equally likely to select, because in a simple random sample, right? That's how it is designed. Each is equally likely to be selected. So 1 out of 10. All right. Now, something that we need to be very considerate of is bias. Bias occurs when a study or experiment fails to represent the population value. And this can be unintentional, okay? So bias can occur not with any sort of malice or intent to skew data, although that does happen too. So let's just talk about some of the kinds of bias that appear in studies. One is sampling bias, when some members of the population are more likely to be asked or surveyed than others. The second kind is voluntary response bias, when you leave it up to the people in your sample to respond. A lot of this comes up when you look at, Yelp reviews or people who are given the option to respond or not respond. Usually people with strong and more dramatic opinions are the ones who choose to respond, so that can skew or give you biased data. Another type of bias is self-interest bias, when claims are made but no data is supplied, and it's evident that the researcher has an interest in the outcome of the experiment. Now, this would be intentional bias, okay? Also, social acceptability bias, when people are hesitant to report the truth because it may reflect negatively on them. So if you think about, if people were surveyed to ask how many alcoholic drinks they consume a week or what their weight is, people may have a tendency to not report accurate information because they don't feel like their answer would be socially acceptable. Leading question bias, this can occur if a question in a survey leads people to a response. So this is done in a very calculated way where the researcher will pose the question in a particular fashion so that people are more inclined to respond in a certain way than another. And then lastly, there's non-response bias, which is when part of your sample fails to respond. So that can make things difficult because then you have a whole chunk of the population that's not being represented. Okay. Moving on now to 1.3. As I mentioned, collecting a simple random sample isn't always so simple. So we have some other sampling designs that we often utilize, and we're just going to study a couple of them. The first one is systematic random sampling. So in that sampling design, you would pre-assign numbers to the objects in the population and then select every kth observation. So say I were to assign each of my students in my statistics class a number 1 through 45. And I wanted a sample of a certain size. And I would say, okay, I'm going to start with number 3. Okay, are you number 3? Cool. You're student number 3. You're in my sample. And then I'm just going to keep adding 5. So student number 8, student number 13, student number 18, etc. You're all part of my sample. That's one way to do it. So for example, you would select every 48th number starting at 22 until you have the desired sample size. This is much easier to execute in practice than simple random sampling. And the cool thing is it usually provides pretty comparable results. The exception is the presence of some kind of cyclical pattern in the listing of the members of the population. So say for some reason, I don't know why this would happen, but say like on my class roster, normally it's listed alphabetically, right? Say I assign the numbers based on that ordering, but the students were listed instead male, female, etc. Well, if I picked every like fifth student, then there's going to be a cyclical pattern to gender matching up with my sample, and that would create a sample that's not representative of the population necessarily. There might be some bias in that. But this doesn't happen that often, okay? So pretty much systematic random sampling is a good way to go. The other sampling design that we're going to talk about right now is cluster sampling. Okay, so here's what happens. The population is partitioned into groups or clusters. So this is the population here. Okay, this whole thing. And it's partitioned or broken up into little groups like this. All right, all these groups are the same size. Then what happens is a simple random sample of the clusters is taken. So you come through, there's 1, 2, 3, 4, 5, 6 clusters, right? 6 clusters or 6 groups. And I randomly select, in this case, we're just saying, I'm randomly going to select 2 of them. So I ended up picking this cluster and this cluster. There's 6 of them. You know, I wrote the numbers on slips of paper and pulled out 2 of them, something like that. And then you take everybody from each of the clusters, and this is your sample, okay? So notice here, in this cluster, I had members 5 and 6, and in this cluster, 11 and 12, and everybody from the selected clusters goes in here. That's my sample, okay? That's cluster sampling. Stratified sampling is a wee bit different. So what happens is the population is divided into subpopulations. So here's the population, and we divide it into, in this example, 3 subpopulations or 3 strata. 1, 2, 3. Okay. Then from each stratum, a simple random sample is taken and collectively used as the sample. So you come to each strata and you go, I'm going to randomly select 1, 2, however many you need. Boop, that goes in your sample. Then you go to the next strata, strata 2, randomly select 1, boop, that goes in your sample. So you take 1 or 2 or however many from each. You take an even number from each strata, okay, when you make your sample. That's not the same as the clustered, because you see nobody was selected from these clusters in the sample. In stratified sampling, everybody from each of the strata or each of the little groups that are made gets selected in the sample, however many you decide based on whatever you need, okay? Good. And that wraps it up, you guys. So that concludes chapter 1. The next video we're going to talk about in chapter 2 more statistical ideas, variables, data, how to organize your data, etc. So stay tuned.